So today I want to talk about how you compose two functions together. And you have some guided notes that you can take notes on. But basically a composition is where the range of one function becomes the domain of another. A composition basically is like where you take one function, like g of x, and you place it inside another function, like f of x. And so in this case, you're not multiplying these functions together. This is not function multiplication like we talked about the other day. It's actually putting a function inside another function. And what I mean by that is if I define g of x as just x minus 2, just a basic linear function, and I define f of x as, say, this quadratic function, then you could take, like, say we had this limited domain, our starting lineup for g of x. So you put these numbers into the g function, and they kick out, like -4, -3, -2, -1, and 0. And what a composition does is whatever g kicks out into its range will automatically become the domain into the f function. Whatever g spits out, f takes in, and it performs its function magic on it, and that's the final range down there. If we look at this not from a numeric standpoint, where we look at specific points, but from like a picture of what's going on, we have two functions, g and f. And you start out with the innermost function. You always start out with the innermost function, g of x. And we take the domain, we put it into g. G sends out the range, and that range immediately goes into the f function, and it spits out our new range. And so a composition of functions is basically putting a function inside another function. So we have really two ways that we can write a composition. Both of these mean the same thing. The open circle, it's not a closed circle, it's not multiplication. The open circle is f composed with g of x. Another way to write that is using these double parentheses, f of g of x. And the domain of f composed with g is the set of all x's in the domain of g, such that g of x is in the domain of f. And I know that is a mouthful of things to say. And this is the mathematics that, when you get to college, your professors are going to use all the time. But we'll come back and we'll talk about domains. But that's an important thing to have in your notes. So you might want to pause the video and have that in your notes. And we'll come back and we'll explain what that means in, real words a little later. So let me do this. Let me take a look at some examples. Let's just do some problems. So I have two functions here, one defined in red, this f function, and one defined in blue, this g function. And let's compose them with a very specific value of x. So if x is -1, what is f of g of -1? So the first thing we do is we start in the innermost function. We're going to find what g of -1 is. So we put -1, it drops into the g function. What's the g function do? It squares the number and adds 4. So this ends up being 5. Now, that 5, I'm going to grab my pen here, that is now what g has put out of its function. And so now what we need to do is we need to do f of 5. Whatever g puts out of its range falls directly into the f function. And what's f do to the number 5? Well, it multiplies it by 2 and subtracts 3. And so it gives us 7. So that's what f composed with g of -1 looks like. Now, if we switch it, g of f of -1, it's going to give us a chance to see, hey, is the composition of functions, is that something that's commutative? Well, let's check and see what this is. Again, you always start with the innermost function. So we're going to take f of -1. So f takes 2 times whatever you drop into it and subtracts 3, and that gives us -5. So now, whatever f is put out, the -5 is going to be dropped into the g function. So we drop that -5 into the g function, it squares it and adds 4, and we end up getting 29. Now notice we ended up, the final result were two totally different things, and that tells us that the composition of functions is not commutative. Order does matter when you do it. Now, let's take a look at the same functions, but this time instead of dealing with a very specific value, let's deal with just x. So let's take f and compose it with g of x. Let's keep it a generic x instead of a very specific one. So we're going to do f of whatever g of x is. Well, g of x is x squared plus 4. So I drop that x squared plus 4 into the f function. And what's the f function do? Well, it takes 2 times whatever you put in, and what we put in is x squared plus 4, and subtracts 3. And we clean that up, distribute your 2 and combine like terms. That gives us 2x squared plus 5. So what we've done is we have dropped a quadratic function into a linear function, and it gave us that. Now, if we compose it a different way, if we start with f of x, and we drop that into the g function, again, you always start in the innermost set, and you expand your way out. Well, the g function is going to operate on the f function. So we put the f function into the g function. Well, the g function takes whatever it is, 2x minus 3, squares it, and adds 4. Now, again, this is where students always mess this up, and it's always sad when they do it, so don't mess that up. 2x minus 3, quantity squared, 4x squared minus 12x plus 9. And don't forget we have a plus 4 at the end. And that gives us 4x squared minus 12x plus 13. Again, notice that when you change the order of f and g, we end up with 2 totally different answers. Totally different. So, composition of functions, not commutative. Now, if you can compose functions, you can also decompose functions. Notice my hilarious title there, decomposing functions. It's a good one. So some functions you can decompose or break apart. If composing means you put one into the other, decomposing means you break them down into 2 separate functions. And again, this is a topic that is a pre-calculus topic. We'll see how it kind of helps us in this class, but when you get to calculus, being able to take a really nasty, ugly function and break it down into 2 or 3 nicer, cleaner functions is really, really valuable. So let's take a look at how we might decompose this. Now this is a pretty messy function. And so what we can do is we can break this up into 2 other functions. Basically what we're doing is we're going to break f of x apart into 2 nicer functions. We're going to decompose this into h of g of x. So we're going to break it up into 2 nicer, easier to work with functions. So, what's the inner portion, the function we start with? Well, there's a lot of things you can do, but I'm thinking a nice inner portion might be 2x minus 3 quantity squared. It's just a quadratic. And if that's g of x, what's h of x have to be so we end up with this? Well, obviously h of x has to be a fraction. And in this case, we can make it 1 over whatever it needs to be. And in this case, it needs to be 1 over x. And that way, when you compose these functions, we'll put this g function into the f function, into the h function, and it will look just like the f function. Now, that's the first way I did this, but you don't have to do it that way. We could break this thing apart in a different way. Like down here, here's an f of x, same thing. But this time we can make g of x just 2x minus 3. We can make the inner portion just a linear function. And if that's what we made g of x, h of x would have to be 1 over x squared. Because when we put g into the h function, we end up with that. And that's a process known as decomposing functions, breaking them up into smaller things. And actually, we, right now, in pre-calculus, we can use this concept to help us out. Like, what if I asked you to graph this? And you look and you say, well, I see an absolute value. and that's a V-shaped graph. But I also see a parabola, which is, let's just say, a U-shaped graph. How do you do this? Well, some kids feel like, oh, the graph technique's going to fail. No, it's not going to fail. The graph technique, world-renowned technique. It will always work. But here's what you could do. You could say, well, I see two different functions here. The first thing I see is this inner portion, which we know is a parabola. And so you could graph the equation 2 times the quantity x minus 1 squared minus 4. Use the graph technique to graph that. So, you're going to want to first come up with the new origin. Then you're going to want to make your table of movements, and then you're going to want to scale that table of movements. But you end up getting this parabola here. Okay, now that's the inner function. That's the first thing you do. Well, that's not what I asked you to graph. I asked you to graph the absolute value of that. But if we break this apart into two functions, watch what we can do when we talk about the absolute value of this. Absolute values take anything, any number at all, and force them to become positive. So let's take a look at what my first function put out as its range. Well, it put out all these positive numbers. And when I take the absolute value of a positive number, it stays positive. And when I take the absolute value of 0, it stays 0. So all these positive numbers that came out of the first function, that came out of this, stay positive. Well, what's the absolute value do to negative numbers? Well, all these negative numbers have to flip up and become positive. So when we put 1 into the red function, it spit out a -4. Well, when that -4 falls into my absolute value function, it's going to become +4. When I put 2 into my red function, it spit out a -2. But when I drop that into my absolute value function, it becomes +2. So all these negatives down here become positive, and my final graph is that blue graph. Notice it has the pointiness here of an absolute value down here, and it has the curviness of a parabola. And so right now we can see some use for these compositions of functions. They allow us to use our nice graphing techniques in more complicated functions. Now, there's another part of this, which is where we talk about domain. But I think we're going to just put this off for a little while now and talk about this more in a face-to-face environment. So what I'd like you to do, there are some problems on the back for you to do for practice. Why don't you go ahead and pause the video and try those problems, and then come back, and here are the answers right there. Now, I did not include this problem here in this number 2A and 2B. Don't worry about that right now, because I didn't put that in your guided notes. But down here, I gave you some sample answers. Of course, when you decompose a function into two other functions, there's lots of ways of doing that. And these are just some sample ways you can do it. Your homework tonight is on that other sheet. And so what I'd like you to do is, those of you who are in hybrid, have that sheet finished by the time you come physically to school next week. I'm really excited to see you guys. If you're in distance learning, have that sheet finished by the time you are tuning in next week to school. So I am excited to see those of you who are coming face to face. It will be super exciting to finally teach a room full of students. And good luck with your homework.